Thank you. Thank you for the introduction, and thank you all for coming. I think the timing of this presentation is very good because we just had a metadata birds of a feather session earlier today. So thank you, Byron, for setting that up. I think we had some nice talks there. And during that BOF, I talked a bit about this project, which was basically metadata transformation using pygeometa. So I am giving this presentation on behalf of Paul, who's in the Netherlands, not here with us today, but he sends his regrets and his best regards. So I'm presenting it on behalf of the two of us. So as mentioned, I'm with the Weather Service, Met Service of Canada. I'm currently serving on the board of directors. Paul is an SDI specialist at ISRIC, so soil. So here you can see we have meteorology and soil domains. Metadata is important to many different domains, and that's the great thing about metadata, as well as geospatial, is that we transcend all sorts of different disciplines. And so wherever we're coming from, it's a ubiquitous domain. So the way this presentation is going to work is I'm going to give an introduction to the project and what it's all about, and then I'll give a few case studies of its, a few targeted case studies of usage, and hopefully we'll have a little bit of time for some questions and discussions. So pygeometa is a Python package. It is a pure Python package to manage metadata for geospatial data sets. That means creating metadata, updating metadata, and reading and writing metadata for that matter. So I don't want to call it a GDAL for metadata, but it has that type of capability where it does read-write across a number of different formats. It was created in 2009. It was originally called PyGDM as part of a larger geospatial data management workflow and pipeline we had at Environment Canada at the time. And at one point, the thinking was, why don't we pull out this specific part, which is just for metadata, because it was that PyGDM tool, internal tool, had a lot of workflows around actually hitting data and so on. So we pulled out the metadata part and we called it pygeometa in 2014. So that's when it was initially came public, and then we put it onto GitHub per se in 2015. So it's been around for 10 years or so. So the basic architecture of how it works is it is very composable. So you can either run pygeometa as a command line tool. So if you are used to command line and Python, you can say pip3 install pygeometa, and you can run it on the CLI. You can also run it within your own Python application, which means you can use its Python API directly, and you can build out your workflows as you need without the need for CLI. So this is great for doing pipelines, metadata pipelines. It takes a configuration. So obviously, in the pygeometa space, we have an abstract concept or an abstract metadata representation, which we call the metadata control file, and that's realized as a YAML file. So we have a very generic way of describing a geospatial resource, whether it's a data set, a service, a process, whatever it may be. And then using that internal configuration and pygeometa itself, we're able to read and write back and forth from all the different metadata standards. The great thing about metadata standards and the great thing about standards is that there's always so many to choose from. And in one way, it's a necessary evil to have these kinds of transformation tools, because I'm not sure that we'll ever agree or there will ever be just one. And maybe there shouldn't be just one. It's valuable to have different metadata formats are valuable for many different communities, but of critical value is the ability to transform them. So this is what a metadata control file looks like. It is YAML, if you can recognize that up on the screen. So basically it's blocks and indentations and lists and objects and strings and floats and all these things. This is our core metadata format in pygeometa, the MCF file. So this can be an actual file on disk. This can be a dictionary that you would create in your pipeline, and you're sending it along just the same. So what we do from this format is we're able to generate different geospatial metadata from this format. The other thing we can do is import. So we can read an existing metadata file and import it into this structure. So for example, if we wanted to read an ISO file and import it, it would import into this MCF file. The basic idea is that it's abstract, it's just YAML and nothing else, so that plays very nicely with Python, which is essentially dictionary representation. We used to use this Windows INI format which got migrated to YAML format is 0.2, basically because of the ability to do nesting of different metadata constructs. We also support multilingual capabilities. So we can support one-to-many languages in a metadata control file, which is critical path, at least in Canada, where we have 2 official languages, French and English. So we're able to do the I-18N stuff accordingly. Because it's YAML, it benefits from what YAML already gives us out of the box. So with YAML, if you're familiar with the YAML format, you will know that you can do things like anchors and references, which basically mean you can define blocks or templates in YAML and refer to them without actually rewriting them and copy-pasting them. This is super powerful because obviously it's a do not repeat yourself approach. It's dry, and you can use these things across MCF files as well. We have a parent and child relationship and a base child relationship where, for example, let's say you have 1,000 MCF files, but you want to have a single contact for all of those MCF files. You can create a shared MCF file of just the contact information, and then all of the other MCF files can basically include it accordingly. So if you ever have to change the contact information, you would change it once in one of the include files, or base MCFs as we call them, and then you can regenerate. So it works. It has that include type capability, which is valuable for obvious reasons. The format itself has a JSON schema, so at any point in time you can see what constructs we're supporting and how they are put together. So the JSON schema for MCF is valuable because you can do validation of this actual format, this internal format. So just to clarify, the MCF format is not an international standard. It's not a community standard. It is an implementation-specific approach. So, which is probably valuable to keep it there for now. But if you look at the MCF format itself, it looks strangely close to ISO 19115/19139. Because it's my personal belief that you can probably generate anything you want from a 19139 representation. So initially, a lot of stuff comes from ISO in terms of how it is formatted. And because we have a JSON schema, it is very easy to make model-driven user interfaces. So there is a project called MDME, which I think is in later on in the slides, which is basically a web UI that we have available on GitHub that simply takes the MCF JSON schema and it creates all the web forms that you need to do metadata editing and management. Also, a big part of it is supporting in-memory pipelines. We have a lot of workflows in MSC and in the weather business where metadata is created and managed in transmission, and it needs to get to one place to the other without actually putting a file on disk, and we're just streaming metadata across for real-time mission-critical purposes, so it's valuable from that perspective. Because of that, it's also optimal for continuous integration CI/CD type workflows, as well as given that, things that work on GitHub. I'll give a specific example later on in the presentation around how we use pygeometa and GitHub to do CI/CD. We support a number of different dataset metadata formats as well as granular metadata. So ISO 19115 was the initial level of support, and then we started building out from there. We support the WMO Core Metadata Profile, version 1 or version 2, the OGC API records core model, which is part of the specification. DCAT support was recently added, as well as Stack, and there are a number of others there. We also support. I should have mentioned that we also support schema.org for those who are interested. And we also support more domain-specific metadata. So in WMO, that might be a little bit oh, that's cut off, but in WMO, in the UN World Meteorological Organization, we have the concept of station metadata, where we can describe an observing facility and where that observing facility or monitoring facility, where it's located on the Earth, what instruments are attached to that station, what those instruments measure, what their schedule is, and so on. This is called the WIGOS, or WMO Integrated Global Observing System format for station metadata, so we support that as well. The other neat thing is you can come up with you can write your own plugin for your own format. If you don't see any of the formats here, you can write a plugin because it's extensible. You can also propose that plugin to be included in the actual code if you wish, or that plugin can live on its own and you can manage that in your repository, and you can basically load that while running pygeometa at runtime. And basically, we have a abstract base class concept, which if you're familiar with Python, you basically inherit from this class and you write your own functions according to the same signature, and then you go from there. So this is what gives us that extensibility, is that we have abstract base class concepts. If you are writing XML metadata, you can use something like Jinja2, which is a templating library in Python. You can even use E-tree or LXML to accomplish the same thing. Again, in pygeometa, because we have this extensibility concept, it doesn't really matter what you are doing to import or export metadata inside your plugins or inside the pygeometa plugins. It is all encapsulated. The other thing I should mention is we try our best to have a minimal set of dependencies and requirements in the code base. So we always, as a rule, try to be very lean with regards to the dependencies that are required for the project, to keep a low footprint and to reduce the moving parts. So for example, we are using the standard Python JSON library as opposed to something else, because we get that for free with the standard library. Some recent updates, as I mentioned, it's been 10 years since this library's been publicly available. We now support schema.org, but I think I mentioned that. We did a wholesale upgrade to update to Python 3.12. We also added support for something called common workflow languages. So if anybody's involved in data exploitation and Earth observation exploitation platforms, you will know CWL, and we recently added support for reading and writing CWL just the same. We also recently added support for metadata auto detection. So you can ask pygeometa to import something, and you do not have to tell pygeometa what kind of format that is, unless you really want to. It will go through some auto detection and some heuristics, and give you a best guess at what it thinks it is. So that's a neat little feature. Again, all of these are either on the command line or using it directly as a library in your own downstream Python application. So, whoops, that's not good. Did I lose my screen? Okay. So back to this. So YAML. YAML is optimal for version control and Git for that matter. So it plays well with pygeometa. Because we manage things in Git, you can have a fully traceable catalog and history, revision history around your metadata documents. And it's very easy to do search and replace type modifications on your metadata, as opposed to using a full-blown UI where it might be a little bit more interactive, but it does require a little bit more effort. So the goal of the project, again, is like really lean and automated, efficient pipelines. So why is this increasingly becoming important? The project's been around for 10 years, but it started to pick up pace in the last, I would say, 4 or 5 years, because we've seen a data explosion. Because we have a data explosion, we also have a metadata explosion. So this could mean we have static discovery level metadata, or the metadata you would see in an open data catalog, and then we have a lot of momentum data, which requires on-the-fly generation. So imagine in numerical weather prediction, we have the concept of a model run. A model run executes and creates hundreds, if not thousands of files at real time. That needs to be 24/7 mission critical. Each of those files need metadata attached to it on the fly. So it helps with on-the-fly generation of metadata just the same. So we have a few use cases. The first is from Paul. The second one are from other projects that I'm involved in. So Paul, as part of ISRIC, is working on something called land soil crop hubs to enable data sharing in East Africa. And what he's developed is participatory metadata management, which allows users to basically interrogate a catalog, and there is a button on the lower right which says edit me, and this will take you to a GitHub editor, and you can edit your YAML file of your discovery metadata and submit it for a pull request or commit it directly. It all depends on what your workflow is. But the idea there is that you see the record in the catalog, and if you want to update it, it takes you straight to GitHub, and then once it is saved on GitHub, there is continuous integration to push it all along and make it available in the catalog, publishing it to a catalog like PyCSW, for example. So this is a really easy way for folks in that community to get their metadata up to date and keep it managed. Again, the MCFs are hosted directly on GitHub, and then there's CI/CD as well as the classic Git workflow. So reusing a lot of similar things that we're all used to help us manage content. Another one is the Earth Observation Exploitation Platform Common Architecture, EOEPCA. This is a reference implementation based on the work done in the Earth Observation Exploitation Platform Domain Working Group at OGC. There's a concept of a resource catalog in EOEPCA, and we have the same kind of thing where satellite or Earth observation scenes are arriving in real time, and we're required, we're required to publish collection level metadata or dataset level metadata and product level metadata or granular level metadata, just the same. Or processes, which means a common workflow language, for example. So here's let me see if I can get to the next diagram. So here's the basic idea, is that as resources enter the system, they are piped through pygeometa, which puts it into its internal model on the fly, and then it generates all the outputs it needs to. Currently, this is updated for stack-only output, because in EOEPCA, we've decided that all things shall be stack items as far as the granules are concerned, and then those stack items are published to a resource catalog, making a stack API available and an OGC API records API available through PyCSW. And finally, the WMO Information System, or WIS2, is a data exchange effort from the World Meteorological Organization for exchanging weather, climate, and water data. It has a heavy implementation and a heavy dependence on event-driven. So in the weather community, we're driven by events. Weather data does not happen on a cron or a schedule. We need that information as it happens right there, and 10 seconds is already too late. So everything has to happen in the millisecond. PubSub is great for that. We are standardized on it on MQTT. And the way the system works is when data is published to WIS2, what we do is it's published via MQTT, and then there's workflow to validate the metadata and then ingest it to a catalog. So what we've developed for some of our members are a set of tools which basically allows you to edit all your metadata records on GitHub in a Git repository. And once you hit save, it will go generate all those records in real time and publish them, each of them, to an MQTT broker, which is connected to the live network, all on demand. So there's a no-code workflow kind of approach where, again, managing it on GitHub, and as MCF records, native MCF records, and then we set up GitHub actions to convert them to the WMO Core Metadata Profile version 2, or WCMP2, and then it takes that WCMP2 streaming in memory and it sends it to an MQTT broker with the appropriate credentials, obviously, and then from here everything takes over and it gets published to the network. Another workflow that we have is actually, this is the workflow that we have with that I mentioned. So we have a metadata management in the gray. It publishes the metadata to the message broker that's connected through GitHub. And then from here, the rest of the WMO machinery, the registrar, if you will, of our catalog, ingests that metadata, validates it, and publishes it to the catalog, and it's made available via OGC API records and PyGeo API in this case. So really low barrier way for countries to manage and publish their weather, climate, and water data sets using metadata. So takeaways from this presentation, I think we're at time. pygeometa is and always will be a very small, lightweight, and very composable metadata management utility. Whether you want to read or write different geospatial metadata data sets, it's extensible. It uses the MCF and more so the YAML concept to be able to reuse things that are done by broader industry and put a geospatial flavor on it. And it's especially great for Git or GitHub type management and CI/CD workflows that can facilitate OGC API records or stack APIs or any type of search API capabilities. And just for composability's sake, I always show the Unix Magic poster, which is it's a small tool. It does one thing, and it does it well. So when you put all these tools together, you can make magic happen. So kudos for that one. Here's some links on related projects that I described earlier, and I think we're at time. Thank you for your time.
Great. Thanks, Tom. Do we have any questions in the audience?
Yeah, thanks very much, Tom. How easy is it to extend the existing standards with, I don't know, a new standard or an extension to that? So in Australia and New Zealand, we have the ASIC standards, which are an extension on 115. How easy would that be to build into pygeometa?
Good question. Basically, you would create your own Python file as part of the library, and you would define you would define it based on the abstract base class, and you would have an import function and a generate function, and that's that. You would return either a string or an object based on what the output is, and that's pretty much it. Then you would use the command line or the library to inject that new library, that new format, input or output into pygeometa, or you can propose it to the project and get it merged and approved and so on, and then it's made part of the core. So that's basically it. It's one file. Alex.
Thank you. Two questions. Can you use pygeometa then also to transform between, let's say, ISO to OGC API records?
Yes, you can. What it does on the fly is it will import from the one format into MCF in memory and then output the other one. Yes,
okay,
you can.
but you would you go via MCF anyway. Okay,
yeah.
And for stack. Would you also have a stack representation of an MCF representation of stack items? Could you then also at least fill parts of an ISO or OGC API records from a stack input or something like that?
You could, yeah. Then you can just go the other way. So you can have a stack item and send that into MCF to transform an OGC API record or a DCAT or what have you. Yeah. For sure.
Thanks, Tom. You talked about the editor. Is that just the native GitHub text editor? Or is there another editor?
There is an editor called MDME, so MDME. I will quickly show it here, just so everybody has the URL. That is this editor here that Paul wrote back in the Netherlands. So if you go to osgeo.github.io/mdme, that's the model-driven metadata editor. So basically, this is taking the MCF JSON schema and it's auto-populating a form. So it's pretty bare bones. It's not attached to any catalog, so you're not actually publishing anywhere. It will just allow you to download it to your desktop and so on. But the basic idea here is model-driven UIs based on schemas. Mm-hmm.
Cool. Well, thank you so much for that. It's certainly come a very long way from what it used to be, and it's wonderful to see the tool working in anger on data sets that are live. Did you have one more question, sorry?
I can ask separately.
Okay, awesome. Oh, well, thanks everyone. We'll give us a couple of minutes for everyone to come back, and yeah.
Thank you.
Sweet.